So in this video, what I want to talk about is I want to talk about the ordering of functions. And the reason why ordering of functions in big O, right, when we talk about the big O of a function, is because it allows us to understand which functions are, we'd say, more complex, right? So the bigger the big O number is, the more complex the function is, the more computations it requires to run, right? And so consequently, we want smaller big O in general, right, for our algorithms, but we also want to be able to just like kind of evaluate, right? Okay, evaluate which number is actually larger. Now, what we want to get when we talk about the size of when we talk about big O is we want to talk about the growth of functions. How fast do they actually grow? So as x increases, what happens to f of x, right? Okay, so if we imagine that we've got an xy axis, right? We want to say as we get bigger on the x-axis, what happens to our f of x? How fast does it grow? The faster it grows, the faster the big O number is. That's the idea. The faster that the function grows as we increase x, the bigger the big O number is. All right. So to give you an example, we'll start out with the simplest one, which is this constant function f of x equals 1 right here. Okay. So come in. And if I imagine my Euclidean plane, right? Okay, here's 1, fx equals 1. And since it's a constant function, as x increases, right? So as I move further and further and further to the right, f of x stays the same. It's constant, okay? So that's f of x equals 1. That actually has no growth, all right? It doesn't increase at all. Now, the next one that we're going to look at here is this logarithmic function, all right? So if we take a look here, we got f of x equals the log of x, all right? And so now I want to imagine I've now got something here on my x-axis because it does matter now. And here's my y-axis. Okay. So when x equals 1, log of x is equal to 0. Okay. And we end up with right, all these values down here. And then as we start to increase, right, okay, log increases, and log actually does grow. It grows very slowly though. So we kind of want to imagine that it does something a little bit like this, right? Depending upon what you're looking at. This is log 2, so it's going to do something along those lines. Okay, so this is f of x equals, this is log base 2 of x, right? So it still is, it's increasing, but it increases very slowly. As x increases, log x also increases slowly. Now what you want to notice is that log x, or log 2x, is actually bigger than log of x. Okay, log 2x is bigger than log of x. And so, because log 2 of x is bigger than f of x as x gets bigger, right? What we say is that log 2 of x grows faster, so it's got a bigger big O number. There it is. Its big O is larger. All right. Now, next up, we've got f of x equals x. Now, if we look at f of x equals x, okay, that's this one right here. It's a constant function. All right. And you'll notice that as soon as I get past x equals 1, so as soon as I get past x equals 1, f of x equals 1, or f of x equals x, is bigger than f of x equals 1. And it's always larger than this f of x equals log 2 of x. Okay, so consequently, f of x equals x has the bigger big O number. Okay, it's larger, right? It's growing faster. Okay, the next one up that we're going to look at on this one, particular one, is going to be f of x equals, we'll hold off on f of x equals x times log x. Let's look at f of x equals x squared. So f of x equals x squared is going to look like this. Right? It's a parabola. There's your parabola. Now here's the thing. When x is less than 1, x squared is actually less than x. And you can kind of see that. You can take a look. Because if you square a fraction, right? Okay, if you square a fraction, then what you're going to get is you're going to get a smaller number than the original number. If you square something that's bigger than 1, then what you do is you end up getting larger and larger and larger numbers if you square a number bigger than 1. So that's the deal, right? Okay. If I have a number that's less than 1, I'm squaring a fraction, so I'm getting smaller. So less than 1, when x is less than 1, we have x squared is actually less than x. Okay. But when x is greater than 1, then x squared is greater than x. So when we talk about witnesses, that's why we're going to set our k equal to 1. We're going to say when x is greater than 1, x squared is going to be greater than x. Because if x isn't greater than 1, x squared is actually less than x. Okay? Right? Just like, for example, if x is less than 2, then log 2 of x is actually less than x y equals 1. All right? That's a problem. Okay? So we would actually state in that case, our witness would be let x equal k, or excuse me, let k equal 2. So when x is greater than 2, log 2 of x is going to be greater than 1. Okay? And literally we can see that's happening. Now let's discuss x log x. So this fourth one, x log x. And so what I want to do is I want to say, okay, well, if I'd say that x is actually big O of x log x, what I'm saying is that at some point in time, x log x is going to get bigger than just f of x equals x. So at some point in time, I'm actually going to get that function getting larger. All right. And so what I've done is I've opened up something, our graphing technology with Desmos. And the red line right here is actually x log x. And the green line is x. And so what I want you to notice is that up until we hit, right, okay, x equals 10, x, the green line, is above the red line. But as soon as I get past 10, okay, as soon as I get past 10, x log x is actually now bigger, right, is now getting bigger than that green line, okay, and so consequently, x log x gets larger. And as I increase up, as I just increase my function, right, you can see that that distance actually gets larger. So x log x continues to be larger than x as long as, okay, as long as x is bigger than 10. Okay, so as long as x is bigger than 10, x log x is in fact going to be bigger than f of x equals x. So let's talk about why this is the case. So x log x, okay, x log x is going to be greater than or equal to x times 1, right, when x is greater than 10. Well, in our example, okay, we were using a log base 10. So log base 10 of x, right, which is greater than 1 when x is greater than 10. Okay? So if I say, all right, so suppose, so if x is greater than 10, then x times log x, okay, is going to be greater than x, which equals x times 1. All right? So in this case, what we do is we'd set our k, right, that first witness, k equal to 10, right, and then our c is going to equal 1 in this case because we don't have any coefficients in front of our polynomials. But that kind of gives you a sense of like why it is that we're going to choose a particular k. Well, in this case, okay, to make our argument that x log x is greater than or equal to x, we need to make sure that x is in fact greater than 10. So now let's consider the last two here. Let's consider the exponentials and we'll consider the factorial. Okay, so exponentials, right? They're anything that has a base bigger than 1 raised to some x power, right? And they grow very, very fast because x increases like exponentially, right? So the x increases for every value of x. So like, 1, 2, 3. As we increase x, the x in the exponential increases. So it actually increases really quickly, right? X factorial also increases really fast because we're multiplying now by a bigger and bigger and bigger number each and every time. And so the question is like, which one's growing faster, right? Is it our exponential or is it x factorial? So let's go back to Desmos and see. Okay. Now, the blue line here is going to be our exponential. That's 2 to the x. And our purple line here is going to be x factorial. So when I look at 2 to the x, all right, well, let's see. If you see here, like somewhere around here before 4, okay, before 4, right at about the little past 3 actually. So before 4, what I see is that the purple line passes, okay, so they intersect somewhere around here, and the purple line passes the blue line, and so consequently that purple line now becomes dominant. It's the dominant line. That is that it's always bigger than the blue line, and that purple line is x factorial, and the blue line is 2 to the x. So what that tells me is that as long as, and let's just for the sake of security, let's pick an x equals 4, this value right down here, x equals 4, because that way we definitely know that we're past, right, that we're past this point where they intersect. So as long as we choose that x is greater than 4, then x factorial is going to be greater than 2 to the x. Now, if you choose a different exponential, let's see what happens, right? Let's say, for example, I choose 3 to the x. What I'd expect, 3 to the x. What I expect is that x factorial is actually going to pass it much later, all right? Because 3 to the x grows really fast. So with 2 to the x, I've got to say, oh, well, it's somewhere around 4, right? But with 3 to the x, let's take a look. When does it pass, right? X factorial is now past 4, right? We haven't even gotten to 5 yet, though, because these guys grow fast. Oops, still going. But notice how that the two lines actually are getting closer and closer together, right? Okay. Slowly, but closer together. Keep going, keep going. And what that tells me is that eventually they are going to meet somewhere along these lines. I will tell you it'll be before, let's say it's before 10. So if we make sure that x is greater than 10, we're going to get x factorial is going to be greater than 3 to the x. Like I could pretty much guarantee that that's the case. That x factorial will end up becoming dominant, right? Okay, so x factorial actually is dominant over 2 to the x. Okay, so x factorial becomes dominant over 2 to the x. And all we need to do is we just need to specify for what x values. When it was coming to 2 to the x, we said, okay, when x is greater than 4, like once we get past that point where x is greater than 4, then x factorial is going to become dominant over 2 to the x, and we can in fact say that x factorial is bigger. All right, okay? And so that kind of helps us to understand, or I hope this helps you to understand, like where we get those numbers from, like which one's big O, which one, it's which functions are big O of which other functions, is because at some point in time, for some value of x, okay, we're eventually going to have the one function become dominant over the other. Now, one other thing to get here is that it really actually doesn't matter for which value of x. It could be a very, very large value of x, because since we're dealing with, algorithms that are running lots and lots and lots of computations, all we want to do, and on very big data sets, we just need to know as far as once it gets out to some big x, like once it can get way out there. That's why we weren't so worried when we looked at 3 to the x and x factorial. As long as it just gets back there, out there far enough, okay, what will eventually happen is that we will eventually have one function become dominant over the other, all right? And that's how we end up with big O numbers. Okay, that completes this section.